So the power rule basically states that if you have a function f of x equals x to the n, that f prime of x would equal n x raised to the n minus 1 power. Now I get that that can be a little confusing, so let's do a few examples. So let's say that f of x equals x squared. In this case, x is the x and 2 is the n. So, adopting the power rule, we can see that f prime of x would equal nx, so 2x, n minus 1, so we could just put a 1 here, which basically just equals 2x. So, the derivative of x squared is 2x. So our next function will be f of x equals x to the 5th. Now, take a moment and see if you can find the derivative. Anyone? Anyone? April.
Is it 5x to the 4th?
That is correct. So f prime of x equals 5x to the 4th. So this next one is going to be a little more difficult. Let's see if you can get it. F of x equals 2x raised to the negative 50th power. So what would f prime of x be?
Gee, I don't know.
Well, it's important to remember that even when implementing the power rule, the negative rules still apply. So we'd see that negative 50 times 2 is negative 100. So we get the negative 100 times the x, as we can see in the example over here. But then we have to remember that when we subtract 1 with negatives, it would actually be a negative 51, not a negative 49. So we find that the derivative of f of x is that the derivative of 2x minus to the negative 50 is negative 100x raised to the negative 51th power. Thank you for joining me in Mehek's math class and learning the power rule. Here it is. So next on our agenda is the chain rule. Now the best way to look at this, since it is a little bit complicated, is to just go look into the examples. So let's dive right in. So our first function here is f of x equals sine x squared. Now the obvious answer might be 2 sine x, but you'd be incorrect. In this case, we'd have to use the chain rule. So basically the chain rule states that if you have a function, you have to look and see basically it states that if you have a more complex function, you're going to have to split it up and find the derivative of all parts. So for example, right here we'd see that there's a 2 up here. There's the exponent. So we'd have to do the power rule and we'd find that the 2 comes up. So you'd end up with 2 sine x to the first power, or just 2 sine x. But we also have to acknowledge the sine x inside the parentheses. So you'd have to find the derivative of the inside as well, which is cosine x. So you multiply that. So 2 sine x times cosine x. And that is the derivative. So let's do another example. This one's a little more complicated. So here we have f of x equals 3x squared plus 5 raised to the 3rd power. Now we will implement the chain rule. So we find that this 3 comes down, so it would be 3x squared plus 5 to the 2nd power using the power rule. And we would multiply that by this inside function, 3x squared plus 5. And we find the derivative of that to be 6x. So you end up with f prime of x equals 3 times 3x squared plus 5 raised to the 2nd power times 6x. Okay, and the cool thing about that is that you can actually simplify this function. So it would be 18x times the function 3x squared plus 5 raised to the 2nd power. And there you have it, that's the chain rule. Next we'll be learning about the product rule. Now the product rule is used when you have a function that contains a variable multiple times. In this case we have 2 variables, u and v. Now the rule itself can be depicted by a simple equation. Here we have the function f of x equals u times v. So to find f prime, the rule simply states that u times v prime plus v times u prime is the derivative of this function. Okay, so let's look at some examples. The first one here is f of x equals x cubed times sine x. In this case, x cubed can function as the u, and sine x can function as the v. Okay, so we see that this rule states that u times v prime. So we can look at x cubed as u, And the derivative of sine x, which is the v in this case, is cosine x. So that's the first part, and then we have to look at the other side. So we add it, and it'll be v, so sine x, times the derivative of x cubed, which is 3x squared. And there you have it. That's the derivative of this function. Just like the product rule, the quotient rule also has a very specific equation. Now, let me just write it out. So, let's look at an example. So this function is f of x equals x squared over sine x. Now, class, what's the rule?
Low D high minus high D low over low low.
Good job. Now let's do this. So we have low D high, so sine x times 2x minus x squared times cosine x over sine x squared. And there you have it. That's the derivative of this function. And that's the quotient rule. Look, Belen in distress. April, save her!
Oh no! I'll save you, Belen, no worries. I got you. No, Belen, no!
There must be another way.
Oh.
Oh no, Belen in distress.
Oh no!
April, don't panic. We can optimize the situation. Okay, I got this. The river is 100 meters wide, and Belen seems to be 300 meters away. April, how fast can you swim?
3 meters per second?
Okay, how fast can you run?
5 meters per second.
Okay, I got all I need. Here's April, and here's Belen, and we're trying to find how far she has to swim and how far she has to run to get to Belen the fastest. If this is x and this is 100, by the Pythagoras theorem, this is x squared plus 100 squared. The running distance is 300 minus x. So the total time equals the swim distance, x squared plus 100 squared, over her swim speed, 3, plus 300 minus x, over her running speed, 5. And we need to minimize t, time, and to do that we need to find its derivative. Okay, so now we found the derivative of t, and we set it equal to 0 to find the relative minimum, which was 75. Now we need to check if that's the absolute minimum, and we do that using the bounds 0 and 300. As you can see, these are both greater than the relative min, so now this turns into the absolute minimum. So now our absolute minimum time is 66.6 seconds, and to find the distances, we plug 75 into x squared plus 100 squared to find the swim time, and which equals 125, and into 300 minus x to find the swim distances, which equals 225 meters. Okay, I got it. April, you swim 125 meters and you run 225 meters.
Okay. Belen, I got you!
Yay! That saves lives!
Oh no! My ladder is sliding down a wall. I need to know the rates that it is changing to make sure it doesn't hit my trash can. Let's use calculus to solve this real-world problem.
We can solve this using related rates.
What we know about the situation is that the ladder is 10 feet and that the base is moving horizontally at a rate of 2 feet per second when it has reached 8 feet. What I want to know is how fast the ladder's top is sliding down the house when the base is 8 feet from the house. We can solve this problem by relating the rates to each other using related rates. I need to relate the two variables of change. We can call the bottom of the ladder x and the wall y. Let's start by drawing a picture of the situation. The ladder forms a triangle with the house and the ground. Now we can fill in what we do know. We do know that x equals 8 feet and the rate it is falling is 2 feet per second. We also know that the ladder is 10 feet. Using Pythagorean theory, we know that y equals 6 because 6 squared plus 8 squared equals 10 squared. Now we can start solving for the rate that y is falling, which is dy dt. We know by Pythagorean theory that x squared plus y squared is 10 squared. Because this relates our rates, we are going to use it. To start, we must implicitly differentiate with respect to time. We can then move around this equation to get what we're looking for, which is dy dt. Canceling out the 2's, we plug in what we do know. That's it. We now know that the rate that the top is sliding down the wall is negative 8/3 feet per second. Now let's solve another problem. Using the same situation, let's find the rate the angle between the ladder and the ground is changing when the base is 8 feet. First, we must find an equation to relate the rates. Because the ladder is always 10 feet, we can use cosine theta equals x over 10 to solve for the rate of the angle at any given moment. Get negative sine theta d theta over dt equals 1/10 dx dt. Because sine is opposite over hypotenuse, we can go back to our picture to get 6/10 or 3/5. Now we can plug everything into the equation. This gives us the rate that the angle is changing, which is negative 1/3 radians per second. Today we conquered two very popular related rates problems. Thanks for watching.
So suppose an object is moving along a coordinate line, say the s-axis, so that we know its position on the line as a function of t, which is time. And in this case, our function is s of t equals x cubed minus 2x. That's what the function here is. So the position of an object at time t is represented by the function s of t, which gives the distance of the object from its origin.
The velocity of an object at time t is the rate of change of its position. In other words, the velocity is the derivative of the position, or v of t equals s prime of t. Here the velocity of the object is 3x squared minus 2.
Speed is the absolute value of velocity. Similarly, the acceleration is the derivative of velocity and the second derivative of position. And in this case, the graph of position and velocity are related because the derivative of position equals velocity. And as you can see here, the slope of the graph is positive from point A to C.
Okay, so acceleration is related to velocity in that v prime of t equals a of t. So that means that when the slope of the velocity is negative, then
On the acceleration, the values are negative as well.
and then over here when the slope is positive,
The acceleration values are positive,
so the velocity has a horizontal tangent at point D.
which is why it equals 0 here, because the slope is 0. So the object moves right or forward when the velocity is greater than 0,
Which is right here and right here,
or when the slope of s of t is positive.
which is from A to C and from E to G. The object moves backwards or left when the velocity is less than 0 or when the slope is negative.
So when the velocity is less than 0 or when the slope is negative, which in this case it's from C to E. So the object speeds up when the velocity is less than 0 and is decreasing,
Which is right here,
or when the velocity is greater than 0 and increasing.
which is right here. The velocity slows down when v of t is greater than 0 and is decreasing,
So in this case it's right here.
or when v of t is less than 0 and is increasing.
Which is from D to E.
So the velocity goes from positive to negative at point C,
That means there's a maximum at point C because the slope goes from increasing to decreasing.
and then the velocity goes from negative to positive at point E.
That means there's a minimum at point E because the slope goes from negative to positive.
So the velocity goes from positive to negative at point C,
That means there's a maximum at point C because the slope goes from increasing to decreasing.
And then the velocity goes from negative to positive at point E.
That means there's a minimum at point E because the slope goes from negative to positive. So the acceleration graph can determine the concavity of the position graph. And when the acceleration graph is negative,
Then the position graph is concave down right here.
and then when the acceleration graph goes to positive values.
The position graph is concave up.
So similarly, how do you say the word? I can't say it.
Similarly.
Can you say similarly?
Similar. Say similar.
Similar.
Similarly.
Similarly.
Yeah, you're good.
Similar.
Similar.
Okay, you're gonna have to cut this one. Yeah, I'm just gonna.